In this segment, we'll look more closely at the mechanics of closure. Let's start by asking, how does closure work for cases like our adder.js example, where the adder function has continued access to pointer inker even when makeAdder has already returned? Now, the details vary somewhat per JavaScript interpreter, but the basic implementation is pretty well locked down by the ECMA 262 spec. First, JS maintains its runtime stack as a linked list rather than an array stack like Java or C. You've probably played around with linked list implementations of the classic stack data structure in which you push a new item on the stack by adding it to the head of the linked list, just like our linkedList.add function, and you pop it by removing the first item. The JavaScript runtime stack is such a linked list. Each stack frame is a JavaScript object with properties for the locals and parameters and return location, etc. And the stack frames form a linked list with the current stack frame, the active one, at the head. The JavaScript standard calls these stack frame objects execution contexts. And once again, the hash table object is JavaScript's big hammer, used even for stack frames now. Each function call adds a new execution context, the stack frame, to the head of the RTS, and each return removes the top execution context from the head of the RTS. If there are no other references to the removed execution context, then the JS garbage collector frees it, as we've described in earlier lectures. So let's adjust the RTS diagram from our prior lecture as we have down here, showing the situation during the call of makeAdder, about at this line here, creating the adder function. We'll show execution contexts with an RTS next pointer, thus pointing to the execution context that called them, and a TOS pointer, top of stack, indicating the current top execution context. So in our situation, the makeAdder function is currently running, and its execution context is at the top of stack, pointing to the execution context for the main function that called it. And let's give it the name main so we can discuss it now. All the angle bracket names in this discussion are offered as labels for hidden JavaScript data that actually cannot be referred to directly in JS code. So don't try to use the angle bracket names as JS syntax. Those are for the lecture only. Now, if an inner function is created during the call, then that inner function object retains a reference to the execution context of its outer function, in our case, makeAdder. So, in fact, the return of the outer function might not result in the garbage collection of its execution context, or stack frame. Any inner function created and returned from the outer function implies an ongoing reference to the outer function's execution context, preventing garbage collection. Let's diagram that for the call of makeAdder. We already know that at line 4 we have the RTS situation shown here in step A, and let's now add the new inner function object created at line 4. We said earlier that a function is an object with two special properties, and the first obviously is its code. And the second we can now add to get a complete picture of a function object, and this is its scope chain, a linked list of execution contexts, for the moment just one of them, to which the function refers when it needs to find a variable. And from now on we'll show function objects in the diagram in green, as you can see, with properties for the code and scope chain, identified by the made-up names angle brackets code and angle brackets scope. Now, moving forward to the situation after returning to the main function from the makeAdder call, we'll have what's shown in step. The execution context for makeAdder is no longer on the RTS, and it will never return to it. A second call of makeAdder would create a new execution context. But it is referred to from the newly created adder function, and it doesn't therefore vanish. When a function f is running, its first stop for any variables is the current top of the RTS. But if a variable is not found there, then it consults the saved execution context from the outer function that created f, which execution context might long since have been popped off the RTS, but which remains pointed to by this scope pointer. If the variable isn't in the scope context, then the next resort is generally the global space. But note, in more complex examples we'll hit in the advanced JavaScript course, and in one example of the next lecture segment, the outer function may itself have been created by yet another function. And in that case, scope points to the start of a linked list of execution contexts, thus the term scope chain. For now, it's enough to visualize one outer function's saved execution context in the scope chain. But what about functions that are created outside of an outer function at the global level? Even they have one saved execution context, technically speaking. And that's the global space. We can view the global space as the anchor execution context, the last execution context on any function scope's chain. If the variable x is not a local variable, and if it's not in the saved execution context of an outer function, then the next stop, and usually the last one, is the global space. So even in our simple examples, we may have two execution contexts in the list pointed to by the function scope pointer, an outer function's execution context, followed by the global execution context. One might even view the global space as a sort of ground-level function call with an execution context that is at the bottom of the RTS, from which all other functions are ultimately called. Any function created at that ground level has only the global space as its outer function scope. So now the global context will also appear at the bottom of our RTS in the diagram. And since execution contexts must form a linked list, we'll add another hidden member called scope next to each execution context, showing the next one in the linked list of scope. Now, given that both the RTS and the scope chain are now linked lists of execution contexts, it's easy to blur them together. But they are different linked lists going in what you might call different directions. A clear indication of this is that the scope chain may include execution contexts that have long since left the RTS. Each execution context thus has two next pointers, again given made-up names in our diagram. RTS next for the next execution context in the RTS, and scope next for the next one in the scope chain. JavaScript follows RTS next to know what execution context to return to when the current function returns. The RTS next, which I've now added back in dashed lines from the execution context for makeAdder, pointed to the execution context for main. And that's what we return to after makeAdder. JS follows scope next when hunting for a variable name. And the global execution context is at the end of either linked list. If we return from a global scope function, we're back in the global space. And if we hunt down, for instance, if we returned from main here, we'd be back in the global space. And if we hunt down a scope chain far enough, then ultimately we find our way back to the global space. Here's question number 1 in our structure lecture here. If I left, or I did leave the scope next for the main execution context empty here, as you can see, where should it point? And if you're not sure how to answer that, you ask yourself, well, what happens if I look for a variable when I'm running in main? Coming back from a pause there, it really should point to the global context, since that's where we'd look if we couldn't find the variable as a local or a parameter in main's execution context. So we'll add that to it. Indeed, generally speaking, almost all execution contexts have the global scope as their scope next, except in those rare cases we've alluded to, where scope chains get longer than one execution context followed by the global context. And like we said, we'll have one example of that in a later lecture. Okay, and now we're going to move on to question 2 here, which is a little more complicated. We have a body of code here that I'd like you to look at and draw the RTS and scope chain configurations that would be in effect in this code at the point that the call on line 11, the inner call here, is just about to be executed, which of course, if you think about it, presumes that the call on line 12 is in progress. Think about that. Be sure you see what I mean. Include all function objects that would exist at that line 11 time, showing their label them by their function names, of all the functions are named here, and show the scope pointers pointing to execution contexts, including possibly the global context. Show any existing execution contexts labeled by their function names and showing scope next pointers and RTS next pointers for any that are on the RTS. I've given function names to all the otherwise anonymous functions, and so use those to label the function objects and execution contexts. Your diagram should have, at the end of it, 4 function objects and 4 execution contexts, counting the global one. So coming back from a probably long pause there. So the diagram here now gives the answer, and we'll go through this a step at a time. Execution contexts are in blue, and function objects are in green. Now, first we have functions f1 here and f3. These are both declared at global scope, and they have the global context as the only execution context in their scope chains. That's fairly straightforward. Function f3 then begins the actual program execution, and it makes a call of f1. And that stack frame here results. f1 creates and returns function f2. And the execution context from its call remains, referred to by the scope chain of f2. Function f2 is also pointed to by inner in the execution context of f3 as a result of that now returned call of f1, all that being on line 8 here, the code we're talking about. Now, function f4 is declared within function f3. So its scope chain starts with f3's execution context. This is important since it means that f4 can use inner. Then a call of f4 on line 12 results in the present TOS, top of stack, execution context. This execution context does not contain inner, and it is f4's scope chain that makes inner accessible. Technically, the execution context at top of stack would also have a scope next pointer pointing to that for f3, but that would only matter if a function were created in f4 so that f4's execution context was retained. I've grayed that link out to show that it's there, but never really relevant. Now, that diagram in a nutshell has an awful lot of the various closure concepts. Look it through, probably review what I just went through, and be sure you understand every arrow and every box in it. And then the final question 3. Continue this on to the point where print x here is about to be called. And coming back from a pause, what we would need then is a new execution context for f2 to be at the top of the RTS, like that. And, of course, f2 will be consulting the f1 execution context via its scope pointer in order to find x, since the execution context on the stack does not have any local variable for x. No local variable declared in here.